All right, let's take a look at some calculations. And as I mentioned, the calculations here, they're not any more complex than one factor ANOVA. There's just more of them. It's really the same thing, and they'll look very similar to a lot of stuff. The only place where the calculation is different is eta squared, and I'll complain about that later. Um, I'll take this first example. This is one that I use in my intro class as well. It's called. It's from a study called "The Southern Culture of Honor." They examined in this study. They examined the impact of insults on men's testosterone. Rises in testosterone are, of course, associated with aggression. You can ask one of the neuroscience folks; they'll probably verify that. I hope. In this study, what the authors were interested in is explaining why our murder rates are so much higher in southern versus northern cities. All right, so as an example here, first, the participants were classified as being either from the north or south. And I believe that they were, this was from a pool of randomly selected students. The second factor, the participants experienced being bumped or insulted or didn't experience anything unusual. And the dependent variable focused on the change in testosterone level from pre to post. And we'll see that there's actually other ways to analyze these sort of pre-post data. As always with statistics, there's multiple ways to do things. So you can see the null hypotheses. Northerners and Southerners show the same level, so the same increase in testosterone. Factor B, bumped and insulted. I'm sorry, I didn't explain the second factor. In the second factor, what the I'll just explain the experimental setting, and it'll make more sense then. Participants came to the research lab. So imagine that you're in BSS building. You maybe go to Dr. Gaffney's lab. You fill out some questionnaires, and then you're told to take your work down the hall to my lab. In the hallway, there's a large filing cabinet, and somebody's got the filing cabinet open, and they are shuffling through things in the bottom of the filing cabinet, and there's really no room to get through. You come down the hall, one of two things happened. In the first case, the person simply closes the drawer and gets out of your way. In the second case, they slam the drawer, they get up, and they kind of bump you, their shoulder, as you're moving past and call you an asshole. So that's the second condition. The interaction is asking whether Northerners or Southerners reacted differently to this sort of minor insult. And it was the author's beliefs that Southerners are more culturally inclined to take anything like that and escalate. And this is why you hear stories of feuds among families in the South. So here are the different formulas. There's 3 F values. They're based not on mean square between group over mean square within, but the mean squares for each of our 3 effects. So we'll see the format here is really, really, really similar. The degrees of freedom within is now the n minus the number of cells. With any design, you can take the levels of the first factor times the levels of times the number of levels of the second factor, and that'll be the number of cells. So this is a 2x2 design. So we would have 4 cells. The previous example in the last video would be a 2x3 design with 6 cells. You can see the degrees of freedom, levels of A minus 1, levels of B minus 1, and then degrees of freedom A times B is A1 minus B1, or you can think of it as degrees of freedom A times degrees of freedom B. Either of them get you there. The sums of square formulas, again, these will look very similar, except where we had the mean of the individual group, that's now going to be the mean of whatever cell they're in. Similarly, the sample size for sums of square between is going to be whatever cell they're in. And then n of A, that's how many people are in each level of A, multiplied by the first level of A's mean minus the grand mean squared, plus however many people are in the second level of A, multiplied by the mean of the second level of A minus the grand mean squared. And then we see the same thing for B. So these look just like the between group. It's just which means we're dealing with. And then the interaction sums of squares, that's actually just computed by taking the difference between the between and sums of square A and B. You can see the mean square values are really pretty straightforward. Sums of squares over the associated degrees of freedom, just like before, again, which there's just more of them. You can see a small data example here. You can calculate the grand mean, and then we have all the different cell means. And then the factor means, these are the means for the main effects. So the first step here is just getting all those things in order, calculating the means. Again, that's not hard. It's just getting used to the notation. The math is pretty straightforward. Calculating the sums of squares. You can see sums of square total calculated just like we had it before. Each score minus the grand mean squared added up. Then within, the only difference here is that it's each score minus the mean of the cell that they live in. So that is where we get the within. The between is as before, just doing this by cell instead of doing it by group mean, because we have more group means. Then we get to sums of square A. So we've got the overall mean for northerners. Overall, they scored a mean of 4. The overall mean for southerners, overall, they scored a mean of 8. We subtract each of those from the grand mean, square it, and then multiply by the number of people in those those levels. Same thing for B, just using the 3.5 and 8.5 means instead. And then the interaction by subtraction. And the A and the B and the interaction, of course, should add up to the sums of square between. The calculations of the mean square is really not all that interesting. We've done this before, and all of the degrees of freedom are 1 for our effects, so those will all just be the same. And then we can calculate F. You can see our F values. They all look pretty big in general. Anything over about 4 is pretty much almost always statistically significant. Again, to remind you of the null hypotheses, main effect for factor A, no difference between northerners and southerners. Factor B, no difference between bumped and not bumped conditions. And finally, whether there is an interaction or not. The probabilities, I just used R to get the probabilities for our F values. And you can see for both of the main effects, those are well below 0.05 for a probability, meaning we would reject the null hypothesis. Overall, southerners were more aggressive than northerners. Overall, bumped were more aggressive than not bumped. A good question to ask here, though, is that the case for all conditions? Is it always the case that southerners are more aggressive than northerners? And we can take a look at that in terms of a graph in a sec. It'll help us to further interpret this. You can see the interaction is also significant, and we'll come back to that because interpreting interactions is really where it's at with factorial ANOVA. I mean, I've said it many times before, psychology is a science that could be defined by, that is defined by its it depends theories. So, interactions are the ultimate it depends effect. All right, calculations of eta squared. This is a little different. We are using something now called partial eta squared, and I'll talk about this in more detail in a little bit. And you can see what we do with partial eta squared. It's not over sums of square total as it was for eta squared. It's over the sums of square for the effect plus the sums of square within. So what's attributable to the other effects is not in the denominator. And one curious thing that this does is it gives us values that can add up to 1. So we're not talking about proportion of variance explained anymore, or proportion of variance explained out of total anymore. We're talking about proportion of variance explained out of a very specific thing, out of what can't be explained by the other factors.